Okay, this lecture we're going to go into more detail on the microwave background. This is radiation that comes to us from all directions and has been really important for us understanding the universe, so I'll go into some more detail. First of all, I'm Robert Nemiroff, this is Michigan Tech, and you're seeing extraordinary concepts in physics, sometimes called Physics X, being taught at Michigan Tech, where I try to go through lots of stuff, where I try to go and delve into the concepts more than the math. Even if you're not in this class, which I suspect most people out there are not, feel free to browse through the lectures and have fun. If you can read this, go there. Otherwise, you can search on Google for the rest of the lectures or on iTunes. So the microwave background radiation was an interesting story. It was predicted at some levels. One of my favorite stories is that there was, there's, in molecular clouds, there are observations that the temperature was not going below a certain amount. And they just thought, oh, isn't that odd? And what we know now is that those molecular clouds were going to be going so cold they were actually heated up by what we now know is the microwave background radiation. So sometimes there's little clues that people don't think to zoom in on. It was just considered an oddity back then, but it's understood in a greater context today. Other people predicted it. Peebles predicted it in some way. But the big news is that it's actually there, and it was measured by Penzias and Wilson when they were trying to map the galaxy's radio emission with a horn-shaped antenna, which looked just like this. They were finding a strange hiss in every direction. So whenever you do an experiment, you expect the first thing you're going to measure is garbage. So it takes a while to calibrate any experiment. So it probably wasn't a surprise to them that they got some hiss, but what was a surprise is that it wouldn't go away very easily. And they were trying all kinds of stuff to explain why it wasn't going away, and they even cleaned out their horn from pigeon poop, which might somehow have some kind of temperature to make it glow and create that, but even that didn't explain it. So here's a picture. This is in New Jersey. So they would point this all over the sky, and they would keep seeing the same stuff. This hiss. Actually, you can, if you have a television that's not hooked into your cable channel, you can unhook your cable and you can see snow. Part of that snow is the microwave background radiation. Not all of it. Some of it could come from local things. So people, oh, that's just snow, don't worry about that. But if they tried to really track it down and worry about every last iota, they might have been another clue to microwave background radiation. So there are lots of clues. So now we know that when these photons arrived when the universe was 400,000 years old. At that time, the universe was cooling and expanding. The average distance between things was increasing. And it became so cold that electrons started to merge with protons. And when that happens, that makes what's called the optical depth to photons go much lower, which were in the gamma ray region. So previously photons, every time they would try to go out on a trip, honey, I'm going to go for bread and milk, they'd ran into that electron, that charged electron or proton all the time. Couldn't even get to the corner store. But after the protons were cold enough to acquire electrons, which means that they weren't bouncing into other protons and photons so much as to keep losing them again, then the photons could fly free. And then they would just keep going because the density of the universe only became lower and lower, and we see those today in every direction, and that is the microwave background radiation. So for a while, people were really happy just to measure it and say, oh, isn't it great that we know the microwave background radiation? And it was great because it helped us understand the global cosmology that we live. Then we discovered more stuff about it, and I'll get to that. So the Earth is actually moving with respect to the microwave background radiation, and looking at it in great detail can tell us a lot about our universe. So here's the microwave background radiation, which is on the average about 2.7 degrees Kelvin in every direction. But when we look at the microwave background in detail, we find there's very, very small differences. In this direction, it's a little bit hotter. Blue means hot. Sometimes in other places, in this direction, it's a little bit colder. So this actually is one of my pet peeves. Typically, if you heat something up, so if you try to if you have a choice between touching a red hot iron and a blue hot iron, touch the red hot one because it's not as hot. Blue hot is hotter than red hot. That's part of black body radiation. So this direction is hotter in the microwave background, this direction is colder, and what's weird is that We're not exactly sure. We understand it's due to our motion with respect to the microwave background, but we don't know what's out there that's causing us to accelerate in that direction. When we look in that direction, we see some mass stuff maybe around here, a little bit around there, and maybe it's a little bit light around here, but we don't really see a huge mass conglomeration in that direction. We know the Earth goes around the sun at some amount of speed, and the sun goes around the center of the galaxy, and we know that our galaxy is falling toward the Virgo cluster, but none of those point exactly here. So we don't know why. So looking at the microwave background pointed out something that's still under research today. We're trying to figure out exactly why we're accelerating to that space. So what's out there? You can read about this with some of the same text at the Astronomy Picture of the Day, October 8th, 2006. Okay, so as COBE, which was a satellite that circled the Earth because it's hard to get microwaves down here on Earth, took better and better maps, it started seeing that there were hot and cold spots. So this is some of the oldest structure known right there. And that came out to be very useful. But what was understood, though, was that these spots are just a little bit too big to tell us detailed information about our universe. That if we could get a better satellite and look at and resolve these spots much better, then we could see much smaller spots, and we could figure out what universes would create those spots. So when that was realized, there was a race to uncover the microwave background, and the race involved designing of satellites that go around the Earth and deploying telescopes to the South Pole, each of which had better angular resolution than the previous one. And once the microwave background was found to such degree, well, here's another one, Boomerang. These are, again, this is what it saw in the background. This is a big balloon that's going to go up and carry its payload, which I think is here or it could be there, which will look at the microwave background above the Earth's atmosphere, which is getting in the way. You can find out more by going to this APOD. There were steps made by all of these satellites and balloons. The one most quoted was the WMAP, Wilkinson Microwave Anisotropy Probe, which started reporting in the early 2000s. And you can notice that this here is the same if we go back as that there. Oops, no, this one. COBE saw something like it. But if you look at much higher resolution, you see the same cold spot is still there. And you see lots more structure. So then people started running, well, they've already run computer simulations, figuring out if the universe is just X amount of years old, and if it has X amount of regular matter, and well, Y amount of regular matter, and Z amount of dark matter, and all these other variables, and then we run a simulation, what microwave background spots would we find? And they'd look at it and they'd say, no, those microwave background spots have different statistical features than this microwave background that we actually see in the universe. And then some people would say, well, we only have a universe of one, so maybe we got lucky. And maybe we did. But we're happier off trying to find what universe fits best, assuming we weren't extremely lucky in that case. And what we found out that was that a very specific universe had omega of 1, so the universe is flat. It has roughly Euclidean geometry. And that the age of the universe, as shown before, was, let's see, T age is about 13.7 billion years old, and that most of the matter, sometimes this is combined with other measurements, most of the matter is, let's see, density is about, for dark matter, dark energy, which is a strange kind of energy, is about 70%, and dark matter, as I gave last lecture, is about 20%, and is it 25%? Yeah. And then there's other kinds of baryonic matter, like you and me, is just a very small amount. Is much less than that. So we learned a lot from looking at the microwave background. We learned that it can't heat our coffee because it's too dim, too weak. You actually need a microwave for that. But we can learn a lot about our universe. So the most recent satellite up there that's now even better than WMAP is the Planck satellite. So WMAP has now been actually sent off and is essentially non-functioning. But currently, in 2010, we have the Planck satellite, which is going to get even better microwave spots on there. And we're going to analyze the distribution of those and try to determine even more about our universe, which might even be able to tell us which inflationary models are to be preferred and which are not. And with that, I will leave you to it next time, and I will see you then.